So first thing we're going to talk about today is average rates of change, which you have probably done a lot of practice with if you've done your WebAssign for the first couple of sections. That's not for us. So average rates of change, you should be able to calculate the average rate of change from a graph, from a table, or just given a function. When you have a graph, the average rate of change is the same thing as the slope of the line connecting the dots. So, excuse me. So if we just were asked for the average rate of change between the 2 points on this graph right here, and all of these documents I have are in the files section of the Bootcamp, so you should be able to have access to these. And they'll all be of the same format. I'll have a learning objective, a few examples, and then I'll have some links of places that you can go to for more information. So we'll go over the examples. And you notice when I say ARC, I have it defined in several different ways. Change in outputs divided by change in inputs. Change in Y over change in X. F of B minus F of A over B minus A. They're all different ways of calculating an average rate of change. Easiest is just the plain old slope formula. So slope Y2 minus Y1 over X2 minus X1. So in this case, we're going from the point -2, -1 to the point 1, 2. Now, just to prove that it doesn't matter which one I put first, on my document here, I put the point 2, 1 first. This time I'm going to start with -1, -2 on top. And since the -1 came first on top, the -2 has to come first on the bottom. And I still end up with -3 over -3, which is equal to 1. So it doesn't matter which one comes first as long as you're consistent. Now this line that connects two dots on a graph is called a secant line. A lot of the first part of calculus is taking the slopes of secant lines and making them shorter and shorter and shorter and shorter to estimate the slope of the curve at one particular point. Next way we think about average rate of change is from a table. And when we have a table, the inputs are generally in row 1 or column 1. And the outputs in row 2 or column 2. So in this case, I have columns. And they're labeled X and F of X. So the average rate of change from X equals -1 to X equals 2. I'm going to do F of 2 minus F of -1 divided by 2 minus -1. And then I just look at the table. F of 2 is equal to 7. F of -1 is equal to -2. And 2 minus -1 is the same as 2 plus 1. Again, 7 minus negative 2 is the same as 7 plus 2, so it's 9 over 3, which gives me 3. Easy stuff. Works the same if we're given a function, but I am going to give you some little handy tips on using your calculator if you're given a function. So if you want to get your calculator out, you can play along with me. First, I'll turn it on, clear out the old stuff, and I'm going to press the table button. Then I will arrow down to edit function and hit enter. Clear out my old stuff, and I'm going to put in the function x squared plus 2x minus 1. X squared plus 2x minus 1. Now yours may have auto highlighted. If it has auto highlighted, just arrow down to it and then arrow over so that you can do the x equals, because you want to be able to tell it what x values you want. And then go down to calc and hit enter. So we are asked to determine the average rate of change from x equals 3 to negative 3 to x equals 1. So we want f of negative 3 minus f of 1 over negative 3 minus 1. Well, now my table is all ready to calculate these things for me, and you can see I've already done this today because I've already put in negative 3 and I've already put in 1. So I know that that's equal to 2 minus 2 over 4, 0 over 4, which is just 0. So that's a little better than having to plug in 1 squared plus 2 times 1 minus 1 and negative 3 squared plus 2 times negative 3 minus 1. And since these were nice friendly whole numbers we had as outputs, it wasn't too bad for me to just come out here, quit. And if they had been more difficult than 2 minus 2, I could have hit my little fraction button here that lives above the 7 and just put into minus 2 over negative 3 minus 1 and gotten 0. But what if those numbers had lots of decimal places after them and it was going to be really tedious to type them in? I could press my little fraction button and make my calculator look exactly like this. F of negative 3 minus f of 1 over negative 3 minus 1. So to get the f of, I just hit the table button and hit enter. Now it says f of negative 3, close that set of parentheses, minus table, enter, f of 1, close that set of parentheses, arrow down, negative 3 minus 1. And now my calculator does all the work, and I don't have to remember what f of negative 3 was. And it gives me my answer. Questions?
No, I think that's all great. Could you, I'm looking for the files section of the bootcamp and I can't seem to find the document you're working from.
Oh, let's see. Do you have a screen that looks like Math 271 boot camps?
I think I joined Teams from the internet since the link that I had in the calendar invite was broken.
Oh, okay. Let's see. I will post them in the chat. So I'll have to post them as I close them because Word is weird and it won't allow you to share a file that's open. So I'm going to close this file because now we've gone through it all. Here's some more worksheets if you want extra practice and some more videos to watch. Now I can add that to the chat for you.
All right, thank you.
Let's see.
Not sure if that's the reason why maybe others didn't join. I had to go back to the email reminding me about this bootcamp to get this link.
Okay, I will be sure and tell the person in charge that people are having an issue. Okay. Okay. Hit the little. There. You should be able to have it very soon. Okay. And let me do this. I'm going to, next thing we're going to look at was writing the equation of a line. I'm going to go ahead and close that file, and then I'm going to send it to you, and then I'll open it back up. Let's do it this way. File open. There we go. Let's see. Bootcamp worksheets. There's the one I want. Okay. So you probably already have this one open. Equation of a line, and you are going to need to be able to do this because part of calculus is figuring out the average rate of change or slope of a tangent line at a given point, and then you're going to use that and be asked to write the equation of a tangent line. There are a couple of forms for writing the equation of a line. We have point slope form. So y minus some given y coordinate is equal to slope times x minus a given x coordinate. That gives us the equation of a line through the point x1, y1 with slope m. The other is slope-intercept, or y equals mx plus b form, where m is the slope and B is the y-intercept. So it's not often that you're just given the y-intercept. Usually you have to get the equation first into point-slope form, and then if you're asked for your answer to be in y-intercept form, then you're going to have to rewrite it this way. And this is how WebAssign often wants you to write the equation of a line. So we'll start with a simple example where we're given the slope is equal to 7, and we're given a point that we want it to go through, the 0.5 and -2. So just following this format exactly, it would be y minus my y coordinate of -2 is equal to slope times x minus my x coordinate, which is 5. Now, if you didn't need it in slope-intercept form, then you'd be good to go. You could stop right there. Otherwise, you would start to simplify. So minus a negative number is the same as plus. Distribute the 7 through the parentheses, and then just subtract 2 from each side. So the slope is the slope, no matter which form you're in. M stays the same. This particular line crosses the y-axis at -37. Next example just gives us 2 points, the point 1, 6 and the point -2, 5. In order to write the equation, we need a slope and we need a point. We have twice as many points as we need, but we have no slope. So we'll go back to average rates of change and calculate our slope. If I put 6 first on top, then I have to put 1 first on the bottom. 6 minus -5 is 11. 1 minus -2 is 3. So my slope is 11/3. Now you can use either point that you want to in order to get the equation of the line. You could do y minus 6 is equal to 11/3 times x minus 1. Then if you simplify that, you would have y minus 6 is 11/3x minus 11/3. Now I'm going to need to add 6 to each side. But on the right-hand side, I have a denominator of 3. So I'd just as well go ahead and write 6 with a denominator of 3 so I can combine those two together. So I'm going to add 18/3 to each side. Because 18/3 is the same thing as 6, so that disappears. And I'm left with 11/3x. 18 minus 11 gives me plus 7/3. I could just have easily used the other point. So y minus -5 is equal to 11/3 times x minus -2. So first I'm just going to get rid of those minuses and change them into pluses. Then I'm going to distribute my 11/3. Now I need to subtract 5 from each side, but I need it to have a denominator of 3, so I'm going to subtract 15/3 from each side. 5 minus 15/3 goes bye-bye, just like I wanted it to. 22 minus 15 gives me plus 7/3, and it doesn't matter which way you do it, you end up with 11/3 of x plus 7/3. Now, in calculus, what you're going to do is you'll be using calculus to figure out the slope of the line. Then you'll go back and use algebra to plug a point, an x value, into a function. Use that to find your x and y values, because y will be the function evaluated at that point, that x value. And then you'll write the equation of a tangent line using point slope form. The other lines we want to talk about are horizontal and vertical lines. Horizontal lines fit that nice friendly pattern of y equals mx plus b. As if you have a horizontal line, remember that slope is equal to rise over run. That's another way of defining slope or average rate of change. What do horizontal lines have? They have only rise, only run and no rise. They don't rise at all. They're a flat line like that. So if this were the point 1, 5, this would be the point 3, 5. X coordinate comes first, 5, 5. And you would also have the point -1, 5. So those would all be on the same horizontal line. So if you did the change in the y coordinates, we'll just go with these 2 points. 5 minus 5 over the change in the x coordinates, 1 minus -1, gives you a slope of 0. So y equals 0 plus 5. Whatever point it goes through, y is equal to that point. And it makes sense because it has 0 slope. It's a flat line. It's not going up, it's not going down. So if we needed the equation of a line that contains the point -1, 5, well, I just gave it to you. That is parallel to the x-axis, because parallel to the x-axis is just another way of saying horizontal. And it goes through -1, 5. You just look at the y coordinate, y equals 5. Vertical asymptotes look like this. And I wrote that wrong. Horizontal asymptotes look like this. They are horizontal lines, so they are horizontal asymptotes. Sorry about that. And we'll talk about a horizontal asymptote in a moment when we start talking about graphs. The next question asks about being parallel to the y-axis. That's another name for vertical. So what would the slope be of a vertical line? Remember, slope is rise over run. Well, a vertical line has a whole lot of rise. It rises, but it doesn't run at all. So if you tried to write rise over run, you would have something over 0. And you know we can never ever have a 0 in the denominator. So this is undefined slope. Vertical lines have undefined slope. They are of the form x equals whatever x value you have. So if we want it to go through -1, 5, then it would just be x equals -1. And this is what vertical asymptotes look like. You're going to see them often where denominators are equal to 0. If you have a rational function that has 0 in a denominator, you're often going to have a vertical asymptote. Horizontal asymptotes are usually associated with end behavior. Rational functions often have horizontal asymptotes as x approaches positive or negative infinity. They get closer and closer to some number. Okay, questions about writing down equations of lines? Okay. Let me go ahead and see. Next thing was factoring. I'm just going to close all of these Word documents down. And then I'll share them with you one at a time as we get to them. Factoring quadratics is something you are going to be doing all semester long. And I know you've learned to do it, but it may have been a while, so we're going to refresh ourselves on it. And we're going to start with the simplest of all is when we have just a plain old 1 as our leading coefficient. And not only that, but to even make it simpler, we have nothing but plus signs. So leading coefficient of 1. I'm going to write LC for leading coefficient equals 1 and only plus signs. So something like x squared plus 5x plus 4. We open up our parentheses. In order to have that 4 be a positive number, it absolutely has to have a positive times a positive, because this number is positive. Because factoring Our trinomial comes from foiling these two things together. If we foil these two things together, we're going to multiply these two numbers to get the 4, and then we're going to add them to get the 5. So we need two numbers whose product is 4, whose sum is 5. Well, 4 is equal to 2 times 2. 4 is also equal to 5 times 1. 4 times 1. 4 times 1 is the winner. Okay. Leading coefficient is 1, and we have the pattern of minus plus. So the constant term is positive, but the coefficient on the x term is negative. Well, since the constant is positive, that means that the two factors, the two numbers, have to have the same sign. And since this number is negative, the coefficient of our x term, in this case, x squared minus 5x plus 4, I need two negative numbers. So I ask myself the same question. Two numbers whose product is 4, whose sum is 5. This time it's minus 4 and minus 1. So easy stuff. If your constant is positive, then each of your factors has the same sign in the middle. If your constant term is negative, in order to have a negative number here, you have to multiply something positive by something negative. So instead of asking yourself for two numbers whose product is equal to this middle term, you ask for two numbers. Instead of asking for two whose sum is the middle term, you ask for two numbers whose product is 4, whose difference is 3. And again, the winner is 4 and 1. Now, which one gets to be positive and which one gets to be negative? If this number is negative, then the bigger thing gets to be negative. So 4 gets to be negative, 1 gets to be positive. If we have x squared plus 3x minus 4, we ask ourselves the same question, but this time the bigger number gets to be positive. So x plus 4 and x minus 1. Those are the easy ones. Those are my favorite quadratics to factor. What if that leading coefficient is not equal to 1? Well, I say here there are two different ways we can do it. We actually figured out another one in my first boot camp using our calculator to do it. So we'll show you that method too. If we're lucky, then we have something like 2x squared plus x minus 1. We can do this one by guessing and checking, because the only two things you can multiply together and get a 2 to come out are 1 and 2. The only things you can multiply together and get 1 to come out is 1 and 1. So I don't have many options for what goes into my parentheses. I have to have a 2x and an x in order to have 2x squared for my first term. And I have to have a 1 and a 1 in order to have a 1 for my last term. The only decision I have to make is which one gets to have the plus sign and which one gets to have the minus sign. And that's where the guessing and checking comes in. So let's guess. I'll put a plus sign here and a minus sign here. And then I just check. 1 times x gives me x. 2x times minus 1 gives me minus 2x, which gives me minus x. That's not what I want. So I erase that. I changed that minus to a plus, that plus to a minus, and I always check it again. I have minus x, I have plus 2x, and that does indeed give me exactly what I want. So guessing and checking. But what if I have something that's not so friendly, like 10x squared plus x minus 24. So if I'm going to plop down my parentheses, I could have 10x and x. I could have 5x and 2x. But then for that second term, I could have 1 and 24. I could have 2 and 12. I could have 3 and 8. Holy crap. I could have 4 and 6. That's a lot of guessing and checking, and Mama ain't got time for that. So I would use what's called the grouping number method. And it takes this trinomial and transforms it into a 4-term polynomial, and then we use factoring by grouping. So we take the leading coefficient times the constant. So 10 times negative 24 is equal to negative 240. And now you're back to asking yourself that question that we asked back for the easy questions. I need a number whose product equals negative 240, and the sum equals my middle term, in this case, 1. So I'm going to have to think of a plus and a minus, because obviously I'm not going to be doing absolute values like I did before. So I know one number has to be positive, one number has to be negative. So I just need 2 numbers that I can multiply and get 240. Well, sometimes it's really easy. I could just look at it and say 10 times 24. Well, 10 minus 24 would be negative 14 or positive 14, depending upon where you put the signs. That's not going to work. I could have 20 and 12. But the difference between those is 8. So now I'm getting a little frustrated. So what I do is I look at 240 and start thinking of all the different ways I could multiply and get that thing. And there's a lot, because there's all these different factors. So let's try 2 times 120, 2 times 2 times 60. So I'm just taking this, and I'm dividing it by 2 as many times as I can. Two times 2 times 15, 2 times 2 times 2 times 2 times 3 times 5. So 240 is equal to 2 times 2 times 2 times 2 times 3 times 5. Now I can just pick different combinations of 4 2s, a 3, and a 5 until I get one that works. Well, I'm going to pick something easy. I'm going to start with 4 2s and 3 times 5. 2 times 2 is 4, 8, 16. 3 times 5 is 15, and 16 minus 15 is equal to 1. I got a winner. So I'm going to rewrite my original function as 10x squared plus 16x minus 15x minus 24. So I replace that middle term with 2 terms. Then I look for partnerships. I have this partnership and I have this partnership. If I look at 10x squared and 16x, what's the biggest thing I can factor out of those 2 terms? 2 and an x, because they're both even and they both have an x. So that leaves me with 5x plus 8. Now over here I have negative things, and my goal is to end up with 5x plus 8 over here so that I have a common factor of 5x plus 8. So if I look at these two, my common factor would be 3. But since I want positives inside the parentheses, I factor out a negative 3. Negative 3 times 5x, negative 15. Negative 3 times 8, negative 24. So this is equal to 2x minus 3 times 5x plus 8. That took a while. That took some work and a lot of logicking our way through. Now maybe it's test day and you have a limited amount of time. So you think to yourself, my calculator has a polysolve button. I know how to solve this equation. 10x squared plus x minus 24 equals 0 using my polysolve button. So I hit second polysolve. It's a quadratic. I hit enter and I put in my numbers. And again, I've already done it today, so I already have 10 in there. I already have 1 in there. I already have negative 24 in there. I can hit solve. So this means that 10x squared plus 10 plus x minus 24 is equal to 10 times x minus the first 0 that it gives me, 3/2, times x minus the other 0 that it gives me, minus negative 8/5. Well, that doesn't look quite right because it has stupid fractions in it. Nobody wants stupid fractions. Well, if I multiply this term by 2 here, then that fraction would go away. And if I multiply this term by 5, then that fraction would go away. So I'll multiply 2 into this piece, gives me 2x minus 3. I'll multiply 5 into this piece. That gives me 5x minus, or plus 8, because I have minus minus. And there I have factored it. Exact same answer, way less work. So the calculator way, the grouping number way, the guess and check way. Now let's talk about a couple of special things that you should memorize for factoring. A difference of 2 squares. X squared minus a squared. So you could really think of this as one of those easy ones that we started with. I'd need 2 numbers whose product is equal to a squared, whose sum is equal to 0. Plus a minus a. So x squared minus 9, x minus 3, x plus 3. X squared minus 64, x minus 8, x plus 8. Now, ask you, if you had x squared plus 1, how would you factor that?
Would it be x minus 1, x minus 1?
Well, if you have x minus 1 times x minus 1, it gives you the x squared that you need. It gives you the 1 that you need, but your middle term would be minus x. And outers would give you minus x, so you'd have x squared minus 2x plus 1. That was a trick question. This one you cannot factor. It looks so friendly. It looks like, oh, we should be able to factor that. It's no big. No, you can't factor that thing. So if you have a sum of 2 squares, no factoring. Difference of 2 squares, factoring. Unless you want to go into imaginary numbers. We don't want to do that today. Maybe next week, but no, we're not doing imaginary numbers. The other ones that you just need to memorize would be a difference of 2 cubes and a sum of 2 cubes. If you have a difference of 2 cubes, you start out just by writing the terms x minus a. And then you have a minus sign here. All the rest are plus signs. Whoops. Minus plus ax plus a squared. If you have a sum of 2 cubes, then you have x plus a, x squared minus ax plus a squared. So anytime you have 2 cubes, when you factor it, you're going to have 1 minus sign. If you have a difference of 2 cubes, the minus sign goes in the binomial piece. If you have a sum of 2 cubes, the minus sign goes in the trinomial piece, the piece with 3 terms in it. So it's not too hard to memorize. So how you feeling about factoring things?
Pretty good, thank you.
Okay. I'm going to put the last two documents up here, and they're mostly just looking at pictures. Okay, let's look at some polynomial functions. Now, I'm sure that you learned to graph polynomial functions back in pre-calculus. If you took 171 here at Wake Tech, then I know you did, because I've taught 171 a lot. I know what you learned in there. So the important thing about polynomials is if the degree of the polynomial is even, their ends go in the same direction. If the degree is odd, the ends go in opposite directions. No matter what, the positive end, as x approaches infinity, the graph goes in the direction of the leading coefficient. So if you have an even degree, I always think back to parabolas. If you have an even degree and a positive leading coefficient, it's like a happy parabola, both ends go up. If you have an even degree and a negative leading coefficient, it's like a sad parabola and both sides go down. If you have an odd degree, the ends are going to go in opposite directions. And if you have a positive leading coefficient, then as x gets bigger and bigger and bigger, it's going up. So it's like a line with positive slope. If you have a negative leading coefficient, that means that as x gets bigger, your graph gets smaller, so it's like a line with negative slope. So you can always go back to those simplest graphs, the parabola and the line. They behave just like those. And here's the pretty pictures. We have a happy parabola, even degree, both ends go up. Cubic, the right end goes up because the leading coefficient is positive. Right end, both ends go down like a sad parabola. Right end goes down because the leading coefficient goes down and it has odd degree. And hopefully you recall back from pre-calculus that it crosses or touches the x-axis when the polynomial, so we'll call it p of x, is equal to 0. And that depends upon the multiplicity of the 0, whether it crosses or touches. And back in pre-calculus, you probably had to sketch some graphs of polynomials. You knew what the ends did. You knew where it crossed or touched the x-axis. You could plug 0 in and figure out where it crossed the y-axis, but you never knew how high or how low it went. That's what calculus teaches you. Now you're going to be able to figure out where it reaches its highest point and where it reaches its lowest point. So polynomials, you should have a pretty good idea what they look like. They're nice smooth curves. Their domains are all real numbers. You can plug anything into them. You can draw pictures of them without lifting your pencil from the paper. Let's talk about exponential functions. In particular, the natural exponential and natural log functions. E is just a really special number. It's equal to 2.7 ... goes on forever. I don't know what it is. I just know it's 2.7 something. So if we were going to draw this, first off, for the domain, is there anything that I could not plug in there for x? No, I can raise e to any power I want to. So its domain is all real numbers. If I plug 0 in, what is any number raised to the 0 power?
Is it 1?
It is 1. Very good. So it's going to cross the y-axis right there at 1. My very crooked y-axis right there at 1. Now, if I plug 1 in, then it's going to be e, which is 2.7. If I plug 2 in, it's 2.7 squared. So this thing is growing super fast. It looks something like that. That's where the term exponential growth comes from. It really does mean growing really, really fast. On the other side, remember, negative exponents just mean flip me upside down. So it means I'm on the wrong side of the fraction bar, flip it over. So instead of e and then e squared and then e cubed, we'd have 1 over e squared, 1 over e cubed. So we have 1 over stuff that's getting bigger and bigger and bigger. So your graph is getting smaller and smaller and smaller. Now, is there anything I can plug in there? Is there any x that will make e to the x equals 0? No. So it's never going to get to 0. It's going to get closer and closer and closer. It is going to get so close that if you plug it into your calculator, it's going to give up and call it 0. But it's not really 0. It's just really, really close to 0. So this has a horizontal asymptote. And its horizontal asymptote looks like y equals 0. In other words, the x-axis. So as x gets bigger and bigger, e to the x gets bigger and bigger. But as x gets smaller and smaller, e to the x flattens out and approaches 0. Now that's true for any exponential function that has a base bigger than 1. So if you had 2 to the x, or 5 to the x, or 10 to the x, they all look kind of like that. So it's easy to graph an exponential function, b to the x, if b is bigger than 1. They all look something like that. They all approach 0 to the left. They all get bigger to the right. If your base is less than 1, then they flip around backwards. They get bigger to the left and smaller to the right. So something like 1/2 to the x, or 1/3 to the x. They still never get to 0. They're still always positive. They still cross the y-axis at 1, but they just go in the opposite direction. All righty, so let's talk about logarithmic functions. Remember that logs and exponentials are inverse functions. So since e to the x has domain all real numbers and range bigger than 0, that means the natural log of x has domain 0 to infinity and range all real numbers. So you cannot take the natural log of 0 or anything less than 0. You can only log positive stuff. You can try plugging it in your calculator, and your calculator will get angry, and it will tell you that you have made a domain error and won't let you do anything else for a while. So that means if I'm going to draw a picture of it, I don't even need these 2 quadrants over here. Do you remember what the natural log of 1 is? No. Well, you can plug it in your calculator. Let's get out of here. Natural log of 1. Oh, it's 0. It crosses the x-axis right there at 0. Natural log grows slowly, so it looks something like that. And as x gets closer and closer to 0, the natural log function goes down towards negative infinity. So it has a vertical asymptote. At x equals 0, aka the y-axis. And I'm not going to draw the 2 graphs together since I have them graphed right here. You can see they're reflections of each other over the identity line, which is true of all inverse functions. They always reflect one another. So e to the x gets a horizontal asymptote. Natural log of x gets a vertical asymptote. They're buddies. They get opposite stuff. They're like those little twins that don't want the exact same thing, but they have to have as much as the other one has. Okay. More practice if you need it. Let's talk just a little bit about trig graphs. And you probably spent time back in pre-calculus trig drawing lots and lots of graphs where you stretched cosine and sine and you shifted them left and right and you compressed them and you spread them out, and you probably haven't done that in a while and you've forgotten all about it. So let's just kind of go back to the basics. First off, sine and cosine are nice, friendly functions whose domain is all real numbers. And they both have the same general shape. Up and down and up and down and up and down and up and down and up and down. Same general shape. They just repeat over and over again forever. Which means if I try to ask you what happens to cosine as x approaches infinity, you were able to tell me, well, exponential function goes to infinity as x approaches infinity. Cosine, you can't tell me that because you don't know what it does. As soon as you think it's going up, it's going down. As soon as you think it's going down, it's going up. It's just wiggling all over the place. So you have no answer to that. It has no definite end behavior. It just changes its mind forever. So does sine and cosine both. You can't describe their end behavior, but they do vary between positive and -1. We do know their range is -1 to 1. Now, if I want to graph sine, I know that sine of 0 is equal to 0. It goes through the origin. I know the period is 2 pi. So by the time it gets over here to 2 pi, it's back to 0. I know that it's 0 again halfway between because I've memorized my unit circle. Sine is 0 here, sine is 0 right here. And yeah, that looks like a potato chip, not a circle, but that's okay. It's my unit potato chip. Sine starts at 0 and increases. Cosine of 0 is equal to 1. So it starts here at 1. I know that its period is 2 pi. So by the time it gets to 2 pi, it has to be back to 1. At pi, it's equal to -1. So it has to cross the axis halfway between. So cosine starts at 0 and decreases. Graphs don't have to be perfect, but you could sketch out a nice little idea of what cosine looks like just by knowing that sine starts at 0 and increases, cosine starts at 1 and decreases. And now you can go to Desmos and reacquaint yourself with what happens if you multiply something on the outside, say 5 times cosine or sine, it stretches them and makes them go up and down further. If you add something on the outside, it shifts the whole darn graph up. If you add stuff inside, it squishes the period or makes the period longer. So you can go in and experiment with stuff like that. Tangent and cotangent. I don't generally memorize what those graphs look like, except I do know that they have a lot of vertical asymptotes. I know their general shape is like this and like that. I know that tangent is equal to sine of x over cosine of x. So it has vertical asymptotes everywhere that cosine is equal to 0. Cosine is equal to 0 at pi over 2 plus any integer multiple of pi. Cotangent is equal to cosine over sine. So it has vertical asymptotes when sine of x is equal to 0. So that is any integer multiple of pi. 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. And there's the pretty pictures. So if you have a general idea what it looks like, you know it's equal to sine over cosine. You know its domain is everything except these numbers. That's where the vertical asymptotes live. And the range of both is all real numbers. Secant and cosecant. Well, secant is 1 over cosine. It has the same domain and the same vertical asymptotes as tangent. Cosecant is 1 over sine. It has the same domain and same vertical asymptotes as cotangent. So the domain for secant is the same as tangent. They're buddies. And as you get into derivatives, you're going to remember that secant and tangent are buddies, cosecant, cotangent are buddies. They hang out together. They play well together. The range of secant and cosecant, well, since they are cosine and sine flipped upside down, and sine and cosine never get bigger than 1, secant and cosecant never get smaller than 1. So their range is negative infinity to negative 1 and 1 to infinity. It covers everything that sine and cosine don't. Now, as for the inverse trig graphs, most of them I'm just going to let you plug into Desmos and remind yourself what they look like. Remember, inverse trig functions are kind of weird because in order to have an inverse, we have to limit their domain and range. So the domain of inverse sine is just -1 to 1 because the range of sine is -1 to 1. So we limit its range to be between -π½ and π². The most interesting ones are arctan and arccotangent because their domains are all real numbers. So you can talk about their end behavior. As x approaches infinity, the arctan approaches π/2, which is something that's going to be important to you later. So if we look at a graph of that, let me get a Desmos going. Gotta love Desmos. And I'm going to put my y-axis pi. So as x gets bigger and bigger and bigger, you can see it's approaching π/2. Because if I look at tangent of x, and I only look at it from -π/2 less than or equal to x is less than π/. Less than π/2. There we go. They're inverse functions. They are reflections of each other about that identity line, just like the exponential and the logarithmic were. So you take the tangent, you reflect it about that identity line, you get the arctangent, and it has interesting end behavior, which you'll talk about more when you get to those limits. Any questions on anything?
No, this was a great refresher. Thank you.
You're welcome.